So, hello everyone and welcome to this lecture. Till now we have seen some applications of incidence matrix. So, first application was it helped us in finding the number of spanning trees in a graph, right, in a connected graph. Then we see in the last lecture we see how many connected components are there, if at all the graph is connected or not, okay. And then now we will see our one more result, and that result will tell whether the graph has a cycle or not, okay. So, let me state the theorem. It is again very simple, but it will be quite useful later on. So, let me write this theorem. Let G be a graph, let G be a graph on n vertices, okay. The columns, let me write the columns, let me call them J1, J2, J, yeah, the columns J1, let me write with this smaller one, or just yeah, J1, J2 up to Jk, suppose I am choosing k columns, okay, will form an independent set if and only if the columns of QG, we are talking about the incidence matrix, the form an independent set if and only if the corresponding edges, basically you may call EJ1, EJ, basically the edges corresponding to the corresponding edges induce an acyclic graph. Basically it says that, okay, you are choosing k columns, okay, and of course these columns are corresponding to some edges. If these edges, just look at these edges, if these edges are forming or inducing a cyclic graph means there is no cycle in it, only then these columns will form an independent set, otherwise they will form a dependent set. Otherwise means if there is a cycle in the subgraph induced by these edges, so then these edges will then these corresponding columns will form a dependent set, okay. So, let us see the proof of it. Okay, let us do this with first this direction. Suppose the graph is having a cycle, okay, first, and then we will prove that in that case these columns will form a dependent set, okay. Suppose edges corresponding to J1, J2, sorry, up to Jk induced, rather than form I would use the word induced a cyclic graph. Cyclic graph means cyclic graph, I think it's cyclic graph, okay. That means there is a cycle, and without loss of subtlety let me say this cyclic, and suppose these edges basically up to J1 J2, let me put J2, okay, and up to Jp, they are forming cycles. So, P is less than or equal to K here, okay, are forming a cycle, okay. So, the picture will look like this. Basically there is so these are supposed to induce so graph on, okay, so on. So, suppose this is some graph, these are actually, so this will be suppose a big graph G, and inside this is a graph which is induced by these edges corresponding to these columns, okay. And in these subgraphs, suppose this is a cycle, okay. So, let me put with some different color, okay, and number them like this as J1, J2 up to Jp, okay. Now if you see, if you draw the incidence matrix of this whole graph, so QG, okay, and without loss of generality, let me call them E1, E2 and up to EP, right, it will be E4, and there will be directions also, right, because in order to draw incident matrix we always put some directions, there will be directions. Okay, very good. Okay, so now, and how many vertex it will have? So there will be 4 vertices, right, inside this cycle. Very good. Okay, if you write this incidence matrix, there will be, so let me write E1, EP to up to EP, and then there will be some other edges, right. Till now here maybe you can call it K. Okay, maybe I have used the same notation. Yeah, K. Very good. Okay, now if you see this part, only this part, so these edges will be covering only P vertices, right. Right. So these 1, 2 up to P. Okay. So here will be somewhere 1, minus 1, minus 1, 1, and okay, so something like this will, the story will be like, and the part will be 0. And these edges are not falling on other vertices, so this part will be fully 0. Okay. Now think about this. So we have to claim about these columns, right, all. Okay. Now we already know that if you add all these rows, this, it will give you a 0 row. Okay, this will give you a 0 row. That means basically if you take this part, this part, right. So this sub matrix is what? Rank deficient. Basically if you add this is giving 0 row, that means its rank is lesser than P. Its rank is lesser than P, right. If this rank is lesser than P, so we can also show that these rows are, in fact these columns are columns of this matrix E1, EP up to EP, these are also dependent. These columns are also dependent because rows are dependent. See, we have seen that the row rank equal to column rank. Okay, so this is what DIY. Now till here, if you see that if these are dependent, if you just add 0, it doesn't matter. So these up to here, E1, E2 up to EP, all these columns of this matrix QG are linearly dependent. Okay. Now you add whatever rows you add, columns you add to this, right. This whole set will be linearly dependent because you can write them as a linear combination. Okay. Okay, where a linear combination equal to 0 you can write. Okay, so basically this all columns E1, E2, EP will form a linearly dependent set. Okay, so this was very easy part. Okay, now let us move to the other part. Okay, let us move to the other part is this. This is what the converse part. Converse part is what? Suppose the edges corresponding to these are inducing an acyclic graph. Okay, suppose these edges J1, basically edges corresponding to these columns AJ1, J2 up to JP are inducing an acyclic graph. Acyclic graph means there is no cycle in it, no cycle. That means it will be collection of trees. Okay, so it will be collection of trees. So inside this graph, suppose you pick these edges, so this will be like this, collection of trees, collection of so on. Okay, and so on, right. Suppose there are Q trees. Okay, suppose there are Q trees, and these trees are nothing but basically for it they are connected component, Q trees. Okay, and okay, so total, or actually the collection of trees we call forest. Okay, suppose there are Q trees, and let me tell you, let me write this as induced upon acyclic graph F. Okay, F is basically collection of trees. Okay, okay, so suppose number of vertices in F are M. Basically, if you count all the vertices of these graphs, okay, on these edges, suppose this is M. What will be the relation between M, okay, P, okay, I think I have to use this word K here rather than P because P I have used for something else. Sorry about that, sorry about the notation. Okay, so this will be K, okay, and then so what will be the relation between K, M and Q? Remember, if there are n vertices in a tree, how many edges will you have? N minus 1, right? All these are individual trees. Okay, so the relation between this will be K equal to M minus Q. Okay, So out of these many vertices, total number of vertices, you are removing those number of connected components or number of trees, which will give you number of this number of edges. Okay. Our aim is what? Our aim is this. So if we have to prove that these vectors in these column vectors up to jk will basically this form an independent set. Why it is so now? Is it apparent from this part? Is it apparent from this part? This is apparent because what will be the so if you consider on this part, there will be trees, right? There will be trees, that they are disjoint trees. You can now write, because these are the components, right? These are the components. So you can write for this, the QG will be this Q of T1, let me call it T1 up to T2 and so on, there will be TQ. So Q T2 up to QT, yeah, how many? Yeah, Q, right? TQ. Okay. So these columns, so these are the columns, right? J1, J2 up to JK. Okay. Now what is everything here will be 0, right? Everything here will be 0. What will be its rank? Rank we already know, right? The rank will be, what will be its rank? Its rank will be number of vertices minus 1, number of vertices minus 1, number of vertices minus 1, right? So basically this is a full rank, this is a full rank, this is a full rank, right? This is a full rank because the number of vertices, whatever the number of edges will be, that much will be the rank. We have already seen in our previous the lecture that when the graph is connected, the number the rank is n minus 1 when n is the number of vertices, right? So here number of edges will be 1 because these are t, so number of edges will be 1 less than the number of vertices here, right? Okay. So in total this will be a full rank, this will be a full rank, this will be a full rank matrix, and in total if you add this rank, this will be equal to k, this will be equal to k. Okay. So that means this whole matrix is full rank, hence these columns are forming J1, J2 and Jk are forming an independent set. Okay, so I hope you got the answer. So now let me define another interesting matrix, and it will help us characterizing graph into whether this graph is bipartite graph or non-bipartite graph. Okay, so let me first define this matrix. The matrix is quite similar to incidence matrix, and in fact much more simpler than incidence matrix. In incidence matrix there are minus, right? Minus ones, plus ones and then 0. In this matrix there are always all basically instead of minus ones there are ones. Okay, so we call it 0 1 incidence matrix, and it is the defining, this is easier than defining incidence matrix. So suppose take the same graph that we discussed in first lecture or second lecture. So suppose this is your graph. Okay, 1 2 3 4. Okay, now in order to define, there is no need to give direction to the edges. You can just simply just by naming these edges you can draw this matrix E4 E. The matrix is this. Okay, so whenever an edge is falling on some vertex, you put 1 1 to the corresponding vertices, otherwise 0. So for example 1 2 3 4, there will be E1 E2 E3 E4 E5. Maybe I have to make some space for this, and then okay, so yeah, so E1 is falling on 1 and 2, rest is 0. E2 is falling on 2 and 3, rest is 0. E3 2 4, 2 4, rest is 0. E4 is falling on 3 4. You see a very simple one, 1 4. Okay, so now I mean this looks much simpler than the incidence matrix. So we will call it 0 1 incidence matrix. This will help us in determining whether graph is bipartite or not. Okay, so let us start this. Okay, so let me restate the result. The result is theorem. Okay, so the theorem is this. Let G be a connected graph on n vertices. Okay, and let me define this matrix by, let me denote it by M. Okay, on n vertices. Okay, okay, if the rank of M will be, now there are cases, will be n minus 1, when G is bipartite or n otherwise. Okay, so basically by just looking at the rank of this matrix we can tell whether graph will be bipartite or not. Okay, so proof. Let us see the null space of M. Okay, we have already seen the last lecture practice of finding the null space. So what we will do is we will multiply some vector to it, x1 up to xn. Okay, so now you see that instead of 1 and minus 1, now there are 1 1. Okay, whenever there is an edge, so what will be the equation? Equation will be, suppose there is an edge between vertex I and j, the equation will be xi plus xj equals to 0. Okay, okay, first let us see this xi equal to minus xj, right? Now since graph is connected, so basically every mod is some constant. Suppose this constant is alpha for all I. Okay, so this is constant, right? But now suppose you take okay, now suppose inside the graph there is an odd cycle. Okay, suppose, or let us for simplicity take this is a graph and inside there is a triangle. Okay, so what will happen? Okay, now you assign x1, x2, whatever you want, right? So suppose by default, let us say this is x1, this is x2, just assigning, right? x3. There is an edge between x1 and x2, so x1 will be equal to minus x2. Okay, and then again x2 equal to similar to this, right? Again, and then you, because there is an edge, so this will be minus x1. So this implies what? So this implies that all these, so the mod of this we have made alpha anyway. So basically this implies that all these xi's are 0. Basically every alpha is 0. This implies that every alpha is 0. Okay, so this happens, this problem is occurring only when there are odd cycle, right? So when there are odd cycle, this vector is nothing but 0 vector, right? That means in this case there is no independent there are no independent vector in the null space of M. Okay, and so the rank will be full. Okay, so that means this M has the full rank and the rank will be equal to n. Okay, so the rank will be equal to, so rank of M will be equals to n. Again you see the left nullity plus rank equal to n, it coming from that. Okay, very good. So this case is established. Okay, now let us see the case when by the way, a graph is called bipartite if and only if there is no odd cycle. So if there is odd cycle, in that case this was coming to be n. So rank would be for non-bipartite graphs. Very good. Now let us take to the case when G is bipartite. In that case we have to prove that the rank will be n minus 1. Okay, so now suppose G is bipartite. Okay, so that means we can draw this graph as this. There are vectors x, there are vertices x, there are vertices y, and edges are running from there, and so on. Okay, very good, something like this. Okay, idea is now very simple. What you do, you try to, we have to compare the 0 1 incidence matrix with the incidence matrix, and this then the rank is actually quite apparent. So let us do some direction to this from x to y in order to draw its incidence matrix. So if you see that incidence matrix will be what? So suppose there will be on the first part I am writing the all vertices x, in the next all vertices y, and these will be the edges, right? E1 up to suppose m edges are there, right? So you see that up to this part, because these edges are originating from x, right? So there will be ones, right, corresponding to each and otherwise 0 here, and here it will be -1, right? -1, so on, and 0, 0. Okay, and what is your m? M is actually same as this matrix, except that wherever so our part is same, right? And this is y, e1, e2 up to em. Okay, so everything is same. Let me try to make the same stuff. Okay, but here instead of y, instead of -1, there will be +1s. Okay, +1s, so on. Okay, that's all the difference. Now suppose you pick a spanning tree, because this graph is connected, there will be a spanning tree, right? There will be a spanning tree. So suppose you pick some spanning tree here, okay, and suppose spanning tree is on up to this n-1. So suppose there are edges here. Okay, so let me, anyway, so suppose there is somewhere en-1. Okay, now we see that these edges are suppose spanning tree, forming a spanning tree. Now what can we say about these columns? Now since these are forming a spanning tree, remember in the first lecture, due to matrix tree theorem, okay, if you chunk out any window of n-1 cross n-1, suppose this one, n-1 cross n-1, its determinant will be +1 or -1. That means it is full rank. Basically all these columns or chosen rows will be linearly independent. Okay, so the rank of this, at least, so whatever the matrix you choose, n-1 cross n-1, the rank will be n-1. Okay, so that means what? All these columns, okay, columns are linearly independent. These are linearly independent. Okay, so the rank of this will be, this part will be at least n-1. Okay, now keep on adding edges, columns to it, right? Still the whole matrix will have rank, at least the rank of Q is always greater or equal to n-1. Okay, I hope this is clear. But now what about the rank of this? Now you see that the columns, if you pick the columns, the same columns, n-1 columns here, right? n-1, these columns only here if you see that, or maybe you choose any window of n-1 here, n-1 rows here, these rows are only differ by the signs. Okay, so basically these rows are just a scaled version of this. Okay, scale means you are just doing the negative. Okay, so whatever linearity follows, the same thing happens here. Okay, so basically the maximum number of linearly independent rows is same as the maximum number of linearly independent rows here. Okay, so the rank of this matrix and this matrix must be same. Okay, so basically the rank of M is also greater or equal to n-1. Okay, now but we have to still prove that rank is indeed n-1. Okay, rank of M is indeed n-1. So let us see this. So let us see the null space of M. Okay, so if you draw M, so suppose this is M. Okay, so now what you do, you pick a vector where the, suppose till the, here it is all 1. So this is actually corresponding to the vertex which belongs to x. Okay, so this is basically the number of vertices in x. Till then this will be 1 1 1, and otherwise it's, suppose this is -1 -1. Okay, so this is up to mod y. Now this vector, if you multiply by this, right, this is non-zero vector, right, this will give you what, because there are 1 and 1 and all the edges are running from x to y, right, so this will give you 0. Okay, sorry. Okay, so basically there is a vector sitting in, non-zero vector sitting in the left null space of M. So rank will be at most n-1. Okay, so rank will be at most n-1. This means rank of M, this means rank of M is equal to n minus 1, and this completes the proof. So the result is, if the rank is n minus 1, rank of M, the 0 1 incident matrix is n minus 1, the graph is bipartite, otherwise the graph is, and if the rank is n, then the graph is non-bipartite. So thank you very much, yeah, and see you in the next lecture.